In this example, we're going to define a model to be executed using the run analysis only. To do that, we first create a folder called partition. We then create another folder named solution. Inside the solution folder, we will create another folder called zero plastic, in which we're going to store all the recorder solutions. Similarly, in the partition folder, we're going to create a file named plastic zero length.o.json. In our JSON file, we start defining our global variable, in which we're going to specify the number of dimensions of the model, the number of degree of freedoms that is going to have, the mass form and the solution that we're going to employ, and the number of total degree of freedom. We then define the materials that we're going to create in this model. In this case, it's going to be associated to the tag number 1, and it's going to consist of a plastic 1D-J2 material. The properties of the materials are going to be provided in the attributes field. In a similar way, we define the nodes for which we specify the tag number 1. We create this node with 2 degrees of freedom, and the total degree of freedom list in this case is going to be 0, 1, and the free degree of freedom list is going to be associated to -1 and -1, because we want this node to be restricted in x and y direction. We also provide the coordinates in chords as 0, 0. We do the same for the second node, which is going to be associated to tag number 2, and we are going to provide it with the free degree of freedom list 2 and 3, and the free degree of freedom 0, -1 in this case, because we want it to be restrained in the vertical direction. Similarly, the coordinates is going to be 0, 0. We then define the elements, and for that we associate the first element with the tag 1. We provide the connectivity of this element to be between node 1 and 2. The attributes of this element are going to be the direction in the x direction, and the material is going to be 1. And then the element that we're going to create is going to be the zero length 1D element. In a similar way, we provide damping. In this case, we're going to assume free damping, as it's done in this part. And we provide the list of the elements that are going to have this damping. We create a load in the loads tag, and the first load that we're going to create is going to be a point load. The attributes of this load are going to be given by the name, which is going to be a time series, a file, which is be located in the following path, where the time varying loads are going to be loaded, and the list of nodes which are going to be loaded in this case is going to be the second node. The direction of action of this load is going to be 1, 0. It means that goes to the x direction. And then we create a combination in order to be associated to the simulation that we want to solve. In this case, the combination is going to be called zero plastic, and the load that we're going to combine is going to be the load we have defined, in this case the load number 1, and the factor, the combinational factor, is going to be 1.0. We then define the recorders in order to output some solutions. In this case, we want the stresses to be output, and we want the solutions to be written in the stress.o.out file. We're going to take samples every time step, and this recorder is going to be associated to the element number 1 given in the list. We define a second recorder, which is going to store the strings, and these values are going to be recorded in the file strings.o.out. We're going to sample the solutions every one time steps, and we're going to associate this recorder to an element, which is going to be the first element provided in the list field. We then create our simulations that is going to solve the combination that we assign in the tag number 1, and this simulations is going to be done using a dynamic analysis as provided there, which is going to be solved by 201 time steps. The integrator we're going to use for this simulation is going to have a time step of 0.025. We define some tolerance in order to assume that some values are smaller or can be set as 0, and we are going to use a Newmark integrator. We are going to define an algorithm, and since this analysis is nonlinear, we're going to define a number of steps of 50 in between each time step. We're going to provide the convergence test in order to accept the convergence of the solution as the test number 5, and the tolerance is going to be 10 to the minus 6. The algorithm we're going to use in this case is going to be Newton, and the solver in order to solve the linear system is going to be use the eigensolver that is provided in SVL. In order to execute the JSON file we have already created, we open up a terminal windows. Inside this window, we provide the path where the Seismo-VLAB executable is located. We then provide the path where the partition folder is, and finally we provide the name of the JSON file that has to be executed. Once we hit enter, we will see in the solution folder 2 files will be created. The strings.out and the stress.out. If we open up these files using any editor, in this case the Visual Studio Code, in the first 2 lines of this file, some global information about the recorder is the number of recorded elements, then the total number of degree of freedom, and the number of time steps, the element identifier, the number of integration points, and the number of material responses. The values provided in these columns are actually the time varying strains. In a similar way, in the stress file we have the same structure.